It's great to be here this morning. Feels like I'm in Silicon Valley here, guys. We got food trucks outside, got some espresso, all these tech companies out in the lobby. Feels really good. We've got a few slides we're going to pull up here in a second to tell you a little bit about the journey. Oops. 1 second. There we go. Tell you a little bit about the journey we've made over the last couple of years in computing. And what I wanted to do was reflect a little bit on where we've been in computing over the past few years, where we are today, and I think we're in a state of exciting transition where there's a lot of the old way of thinking about software and hardware and the personal computing experience, which is changing. And what Michael asked me to talk a little bit about today is how we see all of this unfolding over the next couple of years. So my story actually will begin back Christmas Eve, December 24th of 1967. A lot of people ask me how I got into NASA and why I left NASA and how I became an entrepreneur. And this photograph actually has a lot to do with it in a lot of different ways. This was snapped by astronaut Bill Anders aboard the Apollo 8 spacecraft. And this actually wasn't a photograph that was on the list of things to do during that mission. Looked out the window of the Apollo spacecraft and just decided to take this picture. And this actually turned out to be one of the most important pictures ever taken, the picture of the Earth from the moon. And it really ignited a whole, back in the 60s and the early 70s, it ignited a whole focus on the Earth and the planet, because this is the first time we've really seen our planet as this fragile blue marble floating out there that, in the middle of space. So I guess the point here is a lot of things that you don't plan on, a lot of things that aren't on the agenda tend to happen, and they tend to have a huge impact on things. And I had this photograph hanging in my room when I was a kid, just looking at it. So it was very inspiring. And so one of the most inspiring photographs ever taken wasn't even on the list of things to do by the astronauts. So when I grew up, I grew up in the age of computers and web browsers and the internet, and we had a tremendous amount of data that every time NASA flew a mission, all that content was coming back and it was being stored on servers. And the servers were back in some scientist lab, and there was a lot of work that was done really behind the scenes, and then every now and then they'd publish a photo. But the American public really didn't have a way to experience NASA's mission. And I had the opportunity to join NASA, first to put a partnership together with Google to take a lot of this data and make it more accessible to people. So we actually worked to put together a team where we took a lot of the data from JPL and some other NASA missions, and we integrated it with a team from Google, on the Google Earth team, to create Google Moon and Google Mars. And so this is actually a screenshot from Google Mars. It's the Victoria crater on Mars. It's actually 3D, so you can fly into the crater and you can see the same kinds of resolution imagery, and in fact we've injected it with all this content from Mars Curiosity and the various Mars rover missions, which you're going to hear a little bit more about in a second. And the thing actually came together in a really amazing way. I mean, you can just basically select Mars in Google Earth, and then you can fly down and you can click on all the different sites where NASA has sent missions, and you can see all the amazing rich content. So this was like probably one of the most inspiring things that I'd ever done and probably ever will do. I mean, this is amazing. This took another planet, and it put it within the reach of 1 billion people that had downloaded Google Earth. And it took all of the data so that everyone can see everything, and everyone can be an astronaut, basically. And in fact, we can even go to Mars, which no astronaut's done yet. So in order to accomplish this mission, I'm a computer guy, so I realized that the way we were doing IT wasn't going to scale at all. We were spending over $2 billion of NASA's budget buying and operating IT gear every year. So to put that into context, that was over 10% of the agency's budget. The budget fluctuates between $15 and $20 billion, depending on various things. So $2 billion is a lot to spend on IT. It was one of the most that any federal agency, other than the Department of Energy and agencies that all they do is collect information. You've heard a lot about that lately. Spend. So we built this project called the Nebula project. Initially, to take advantage of some of the resources we had. And whenever you're in a place, the best thing you can do is try to figure out what resources do we have. Sometimes it's cheap land, sometimes it's everybody has 300 megabit Google Fiber connection to their house. I'm jealous, by the way. We have terrible internet connectivity in Silicon Valley. But in the Silicon Valley at Ames Research Center, we actually had these giant wind tunnels where we tested a lot of spacecraft and aircraft and parachutes from things landing on Mars and such. And they needed lots of power. And so we had really inexpensive electric power to power these giant wind tunnels. We also had a facility called May West, which was one of the first internet peering points. So we had incredible internet connectivity. Just doesn't extend to our homes. No chip on my shoulder there. And we also had lots of land because we're a NASA facility. So we were surrounded by Google and Facebook and Microsoft and all these really big companies. But we had land, which was a rare asset in Silicon Valley. So we tried to figure out how to put as much computing resources in as little space as possible and connect it to the grid, both the internet and the power grid there at Ames. And what you're seeing there is a semi-truck literally pulling in a brick from a data center. So all the servers are actually physically mounted to racks in that 40 by 8 foot shipping container. And that thing is effectively one big computer that just plugs in. And you can basically scale it out just by adding more of the shipping containers. And what we focused on primarily was the software that ran inside of it. At the same time, at the White House, we were really pleased that cloud computing got on the agenda for ways to save money in the government. The government as a whole was spending almost $90 billion across all federal agencies on IT. And this was a tremendous amount of money. There were a lot of very high-profile projects, healthcare, that lots of money was being spent on these websites, and they just didn't work. And this isn't a new theme, right? I mean, there are lots of government IT projects that were going way over budget. It's not one party's fault. It's just the government and its vehicle of contracting to the lowest bidder just doesn't make for high-performance next-generation web design. So when the government started talking about cloud computing as a way of, like, let's not build all this stuff ourselves, let's use some of these cloud services that are being provided by the commercial sector. I mean, the line that I really resonated with was, why in my personal life can I go and get a free Gmail account where I have tens of gigabytes of email when it takes my federal agency 6 months to provision me an email account with 100 megabytes of storage, at a cost of thousands of dollars a year. And of course, Google isn't free. You're being forced to look at ads and stuff. But the point is still the same. I mean, there are enterprise versions of these cloud services that you can buy for a fraction of what the government was putting into these big, massive projects to roll out similar services. So the idea was, let's try to move as much of the federal government to cloud computing as possible. So we actually saw the administration appoint the first ever federal CIO, Vivek Kundra, at the White House. And Vivek rolled out this cloud computing strategy actually out at NASA Ames to highlight some of the work we were doing with the Nebula project, which was exciting. So the first thing that we did was we worked on really the first website, in the first term of the president, which was usaspending.gov. So there were two things that the president really cared about. One was federal transparency. He co-wrote the Obama Coburn Act, which dealt with forcing the government to be more transparent with how it does business. Got that through as a senator in Illinois. And then healthcare. That second website didn't work as well as ours. So we hosted this website on that shipping container and another shipping container out in Goddard in Maryland. And this was a website that literally ingested all of the spending data from every federal agency every day and then rendered it in a way that you could visualize it and see where all your tax dollars are being spent. So you could actually go to this website today and you can select a district, a state, a government contractor, and you can see essentially where all the money's going. So it was a really powerful site. It used all sorts of next-generation scale-out database technologies. It ran on a cloud computing platform. If only the healthcare guys would talk to us. So the president used it. It worked. It was a fun project. I will say that you do not want the White House as your first customer on anything. They're very high maintenance. But then something interesting happened. So we decided to open source all of the technology that we used to build this project. I felt this was a taxpayer-funded initiative. I had a philosophy that why should any government project be closed source? If taxpayers paid for it, taxpayers own it. And owning it, when you're talking about source code and technology, means owning the source code. So what we did is we literally open sourced all the code that we used to power this thing. And a couple weeks later, I got a call from Rackspace Hosting, which many of you have probably heard of. They're a big hosting provider. And they had a similar vision. They had been looking at Amazon Web Services for a very different set of reasons. Rackspace was competing with Amazon. NASA wasn't competing with anyone. We just wanted to have all this cloud computing technology, but we couldn't use a public cloud. I mean, this was back in 2008, 2009, before a lot of the security and compliance stuff had even been talked about. So we were really just trying to take that Amazon Web Services style of computing, bring it inside NASA so we could do projects like the USA Spending Project, like the Google and the Microsoft projects. So when we open sourced everything, we were really pleased at what happened. So we called it OpenStack. And the idea was to take all the technology that allows you to take a whole data center and address it as a set of services and open source that layer so that we could all plug everything into it, and we could all start building on a stack that made everything interoperable, made applications portable between these environments, and would allow us to have a common framework to discuss things like security and compliance. So OpenStack emerged rather quickly. There were a few key projects, core projects. To translate that, basically it was compute, storage, and network services with an identity and security piece that would allow you to figure out who has access to do what, and then a web interface that you can use to interact with it. And it's kind of gone crazy. So over the past couple of years, we just celebrated the 3-year anniversary of OpenStack. It launched in 2010 in July. And we have over 10,000 members now contributing code. It's a nonprofit foundation which has been set up. The platinum founding members, in addition to my company, are HP and Microsoft, and through the SUSE Foundation. Let's see, Dell's involved. Rackspace is, of course, involved. Red Hat's involved. IBM has just gotten very involved. So IBM's entire cloud strategy is OpenStack now. So OpenStack, as a nonprofit foundation, is focused on achieving an industry standard of interoperability between all the different components in the future data center. And that's never happened before. We've always had a single commercial company at the core of computing. Whether it's enterprise computing, where Microsoft had a dominant force, IBM had a dominant force, Sun had a dominant force at one point in time. We have mobile computing, where either Apple and now Google are dominant forces. In enterprise in the future data center, we have a really good shot at OpenStack, which is an open, nonprofit standard of interoperability taking hold as the glue that holds all the pieces together inside the future data center. I think that's really exciting. So you can see the thing's just taken off astronomically. In fact, it's taken off globally. We have our 8th Design Summit, which is being held in a few weeks in Hong Kong, and there are over 6,000 people attending it in Hong Kong. And then we've been doubling every 6 months. I'm not sure how fast we're going to keep that up, but we had 3,000 people in Portland, and then 1,500 people San Diego, 800 people in Boston. So every time we do one of these, and we do them twice a year, we double the attendance. And so, we're gonna quickly be in Chicago or Las Vegas at some point. It'll have to slow down. So why is this all happening? I think there's a lot of interesting and fundamental trends in computing that underscore this. I mean, you don't just have an open source project to go from 0 to almost every computer company on the planet in 3 years if there's no extremely compelling gap, in the market that isn't being served by this. And I think the gap is that we have a tremendous amount of data that we are creating, generating, processing, storing, trying to make sense of, and it's growing exponentially. And so we have over 4 trillion gigabytes of data stored this year, and you can see the graph there. there's an ever-increasing amount of data that we're creating as individuals. Just an incredible stat, over 500 million photographs are being stored by these 4 websites every day. And it's over 500 million, and it's forecast to be, in 2013, by the way, that's year to date. So we've already exceeded 500 million, so it could be 1 billion photos. And the photos are of increasing resolution. So Google Glass, and there are phones, and there are all sorts of devices that are generating this content. But Flickr, Snapchat, Instagram, and Facebook, and you see Facebook is the lion's share of that, represent just a tremendous amount of content being generated. And the impact on this isn't just on your consumer life, but the impact is on the entire industry. Right? If you're a hard disk manufacturer, your customers are no longer people buying PCs at Best Buy. They're internet companies buying disks and chips and servers to host all this data. 100 hours of video are uploaded every minute. So it's not just NASA that has this problem, right? It's increasingly every company that deals with healthcare records or that deals with insurance data from GPSs in your cars. This is MyFitnessPal. So if you wear a Nike Fuel Band or if you have a sensor, all the new phones now have accelerometers, 3-dimensional accelerometers, and can calculate. In fact, the iPhone 4S actually has a whole chip dedicated to the motion of your body that can store encrypted data about your movements and then make that available to applications through an API. And all this data is being increasingly uploaded to services because that data in your phone doesn't do anything for you. But that data, when you correlate it to other activities, can help you understand, did I get a good night's sleep? Right? When is it a good time to wake up? And so forth. How healthy am I? And so no matter where you look, the world's changing, and it's changing fast. This is the percentage of data that is mobile in all internet traffic. So this shows about 15% of all data is now mobile data. And you can see where the trend's going. In just a year or two, it'll be up to about 30% of all data will be mobile. And this is probably why. This is probably my most compelling and interesting chart. So this shows the computer industry as a function of PCs, laptops, and tablets. And so again, this excludes smartphones. This is just computers, what we kind of roughly call computers. Since 1985, all the way through 2013. And this shows the market share of PCs, laptops, and tablets. What's fascinating about this is last quarter, for the first time, more tablets were sold than PCs. And what's even more interesting is 3 years ago, no tablets were sold. So we go from a market which didn't exist to a market which has exceeded personal computers in terms of the volume of units being sold in 3 years. And that's coming out of laptops, it's coming out of PCs, it's changing the very way we interact with the web and with information. We're now using our fingers instead of a keyboard and a mouse to interact. So it's having a profound impact. And the other thing is, just like the internet companies that are storing hundreds of millions of photos every year, having a hugely disruptive effect on the enterprise computing market, this is having a huge impact on just the chip market and the whole computing market. So if more phones are being sold, every phone that has 32 gigabytes of flash or 64 gigabytes of flash or a 64-bit ARM processor on it means billions and billions of inexpensive flash chips are being manufactured, and the cost is going down on these technologies. And so new companies, you might have heard of Violin and Fusion.io, a company called SolidFire. These companies are able to take advantage of these new trends in consumer technology by building enterprise products to incorporate the volume of chips that are being manufactured for these smartphones. So there'll be disruptions in the way enterprise computing is built. If you guys remember servers that have these 3.5-inch hard disks, now increasingly have 2.5-inch hard disks. And you started to see that as this tipped, and we started to see more laptops sold than PCs. So when PCs represented the volume in the market, more 3.5-inch disks were manufactured. And so 3.5-inch disks, and you can go back decade by decade, and you can see, well, 3.5-inch discs, there were 5.5-inch discs, right? 5.25 or whatever. Every time you see a shift in the consumer technologies and the volume in the market, you see a shift in enterprise technologies because we're not making two sets of things. It's all the same stuff. So I guess the point here is this, okay, that's not really fair. This isn't really the focal point of the computer industry anymore. What we're seeing is a bifurcation between the mobile devices that we're carrying around, wearing, have in our pockets, have in our cars, and these giant, massive, hyperscale data centers that sit behind them. And there's exciting technologies being developed both in hardware and software in both of these arenas that will change everything you know today about computing. One more way to look at it is the pressure in the types of computers that are being built and sold. So this just shows orders of magnitude of what you invest in computer systems. So Samsung, Apple, and many others have wristwatches that now talk to your phones because we find that people like bigger screens, but they don't like to carry big. So they can kind of interact with, okay, who's just called me, who's trying to communicate with me on my wrist. It's a better user experience. So we're actually starting to see really inexpensive devices, Jawbone and other wireless devices that we wear, start to complement an increasing ecosystem of devices that exist on our desks, in our cars, all around us, all the way up to public cloud computers. And actually I took this from a talk from a researcher named Jim Gray, who worked with Gordon Bell at Microsoft and Bill Gates at Microsoft. And I had to do a couple things to update it, because this was originally from a talk in 1996. I had to add a 0 to the bottom, because before that, $100 million was a lot for a computer. But I guarantee $100 million isn't a lot for a big computer these days. Facebook and Amazon and others spend billions of dollars on their data centers. And they're literally one logical computer in a lot of cases. They have different fancy names for them, like availability zones. But in effect, they're big cloud computers. And then on the small end of the scale, we're seeing pressure to have less expensive, more ubiquitous devices that surround us talk to ever larger services in the cloud. And they enable each other. The smaller my device, the more connectivity there is. And that's why Kansas City is a very interesting opportunity because of your Google Fiber connectivity. I think don't underestimate the impact that could have here, because you're going to see services developed for a large consumer audience that has hundreds of megabits of connectivity. So the cloud and cloud services will be much more appealing to people here than, say, people in Silicon Valley that have a terrible internet connection that is unstable and is always going down and is extremely expensive. So you might ask, no issues there. I should be careful. Comcast is one of our investors, I think. And I'll note that they provide my internet connectivity in Silicon Valley, yes. That'll get fixed now. So how does this relate to cloud computing, and what are we doing to address this? So cloud computing, when I was at NASA, we had the opportunity to work with NIST to define what cloud computing was, and I'm extremely proud of this work. A lot of what the government does is a waste of time. I won't go on there, but this is one of the most efficient things the government's ever done. This is a 1.5-page document that defines what cloud computing is. So it's probably the most succinct and incredibly efficient work of government documentation ever. So it defines cloud computing as an on-demand, elastic, shared, metered, and accessible resource, computing service. And what I love about this definition is if you take away any element of it, the whole thing falls apart. You can't have an on-demand, shared, accessible resource if you don't meter it, if you don't take a look at how much people are using it and charge them for it. They'll just use an infinite amount of it, right? So you have to meter it, because the economics are a key part of it. If you have this on-demand, elastic, shared, metered resource, but you don't make it broadly accessible, then you just have a small system and the economics fall apart again. So it's actually a fantastic definition, and there's actually a good article yesterday out on the website GigaOM that talks about fake clouds. And I could not agree more with that analysis, and I think any cloud that works like this is not a fake cloud. I mean, this defines what a real cloud is. So the challenge with this is if you work on computing at your business and you are in the school of enterprise computing thought, this is exactly the opposite of the way you think about computing. Cloud is on-demand, elastic, shared, and metered, and accessible. Well, enterprise computing is on approval, static, private, purchased, and fundamentally inaccessible, right? I mean, every single core tenet of cloud computing is literally opposed by a different philosophy in business. And so one of the challenges that a lot of businesses and people have with cloud computing is it completely breaks every paradigm. When I think about security in a business, I think about locking things down. I think about defining system boundaries. I think about understanding and isolating and putting things behind firewalls, right? I think about literally defining a security plan around a known system boundary. When I think about cloud computing, I think about, wow, every Amazon server is available to everyone on the planet. Hackers in China, Russia, everyone, right? So you have to really completely rethink pretty much everything about how you build software and you design software and you design for security and reliability. So the interesting thing about this is there's a whole new economics in computing evolving. So this is you can't read some of the text here, but on the bottom you see infrastructure investment. So the more money you spend on stuff, basically. And on the extreme right side of that spectrum, you have EMC storage, right? You have VMware, you have Cisco, UCS servers, and very, very high-end, very expensive equipment. On the other end of the spectrum, where you spend almost nothing, but you invest huge amounts in your application, you have services from companies like Google and Facebook and Amazon, where these companies literally spend orders of magnitude less money on infrastructure. It would blow your mind if you knew how much a server costs Google or Facebook or Amazon. I mean, it's not thousands or tens of thousands of dollars, it's hundreds of dollars. And when you have several $100 servers that you literally treat like cattle, and if they fail, you just let them be dead, you don't have service contracts, you don't support this stuff, you design your software to tolerate failure. And it's a completely different paradigm in thinking, where you have to literally take advantage of hundreds or thousands or hundreds of thousands of machines that are all extremely inexpensive, and reliability and performance becomes something that you have to design into your software. You don't rely on the infrastructure anymore to give you these characteristics. So if you think about what this means, and I'll give this slide, I'll give this credit to Adrian Cockcroft, who's the chief cloud architect at Netflix. If you're interested in reading more and you're a developer, you're interested in the deep dive on some of this stuff, Adrian has a great blog. But everything you know about software design is changing to take advantage of this new world. So we have concepts like the relational database. Relational databases don't scale past a few tens or hundreds of terabytes. When you start to deal with hundreds of millions of photographs and graphs of relationships of 1 billion people, you need to completely rethink the way you do persistence of data and information, structured and unstructured. File systems just don't get that big. You can't have a 100 petabyte file system, right? Just the construct of a globally consistent namespace becomes theoretically impossible to maintain. And there's a whole theorem about this called the Kemp theorem that basically says, you can have a couple of these characteristics, but you can't have them all. You can't have a globally distributed, globally consistent, highly available system. You can't have all three of those things. So you have to make choices. And so I think the choices need to be made in the applications of the future. And you see here a list of technologies on the left. In-memory sessions is a great one. You can't rely on session data when you have hundreds of millions of users or millions of users. You can't just put the session data in one server and then back that up to another server. There isn't enough memory in that server, but you have to partition it. You have to distribute it. Now the good news is there's a whole, as you think about scaling computing out like this, there's a whole set of technologies which have been open sourced by the large internet companies. So if you're thinking to yourself, oh, that sounds really like something I don't want to go figure out. The good news is in a lot of cases you don't have to. You can go and download a lot of these open source packages. One of the most interesting ones Facebook just came out with, it's called the Presto engine. It's essentially a structured database that operates in memory and on disk that can query 100 petabytes of data in 100 milliseconds using a SQL-like structured query, which is incredible. I mean, the performance and the speed there. So there's a new generation of cloud computers. My company has a platform called Nebula, which connects hundreds of cheap servers together and turns it into an Amazon cloud. What we're seeing here is a progression that has been happening over the past few decades. And about every decade, we've seen an evolution of complexity of systems design, both in consumer technologies and in enterprise technologies. And I think we've gone from mainframes to minis to personal computers to internet computing. And the thing that's happened here, interestingly, is it's all about connectivity. The global connectivity is driving all of these architectural changes. We would not be able to have cloud computing. We would not be able to have these mobile devices so pervasively in our personal lives if we couldn't connect reliably to these services that were hosted elsewhere. And so this new trend of everywhere computing is truly enabled by the connectivity that folks like you guys enjoy here, and maybe someday we'll have in Silicon Valley. And I think it's a very exciting time to be doing what you guys are doing. I think there's a whole new opportunity for disruption. I actually spent, when I got in last night, we had dinner with some of the other speakers and some of the folks that are here. I spoke to a gentleman from an electronic healthcare records company. I'm sure you guys can't figure who that is here, based in Kansas City. And I was delighted to learn that they're figuring out new ways to take all the data and use technologies like Hadoop in very large clusters to correlate the data and to derive value from the data. You'd be surprised at how few companies in the Fortune 1000 have intentional strategies to do this. Many do, and there's a lot of pioneering work happening in this, but many don't. And I think there's an opportunity for any company that embraces the change that I've just talked about today, that looks at how Google and Facebook and Amazon run their data centers and realizes that's them someday, right? That every company, no matter what you do, if you're a shipping and logistics company, you're going to be putting RFID sensors in packages and tracking literally every interaction they have and optimizing every single employee to maximize efficiency. If you're an electronic health records company, you're going to be trying to figure out how to take all this information from sensors and devices, information people are willing to share, and you're going to try to be a better company to better service your customers by better understanding them with all this data that's being collected.